whenever we have the natural base e, all e is just a letter that represents a number, okay, that is the same number every single time. So instead of like x to a power or y to a power, e is always going to be the same number. Okay? It is the natural base e that'll be a big part of whenever we get into logarithms and things like that. So whenever we have the natural base e is the natural number. It's like 2.71, so on and so forth. It's a lot like pi. Okay? In terms of it will never stop. Okay? It will continue on and on. It'll never repeat. It'll never terminate, just like pi. Okay? It's the same idea. Pi represents what you all call normally 3.14, but it just continues on. Same way with e. So whenever we have exponential growth and decay, similar to what we quizzed over yesterday, like where it's y equals 1.2 to the x power, is that growth or decay? It's growth. How much is it growing by? What percent? 20%, right? If it is 0.78 to the x power, like on 2, what is it growth or decay? Decay. It's decay. How much is it dropping by? 22%, right? Okay, or 0.22 or 22%. Same way, whenever we have 5/8, it would be decay. If it's 1.03, it would be growth, so on and so forth. So whenever, just to make sure that we have all of these down, whenever we have the formula for growth and decay, remember that growth is a times 1 plus r to the t power, and decay is a times 1 minus r all to the t power. R is still your rate. We have to change it to a decimal. T is your time in years. Whenever we do compound interest, bless you, you have A equal to the principal times 1 plus the rate divided by the number of times per year, all to the n times t power. Remember, n is your number like quarterly, annually, semi-annually, monthly, stuff like that. T is still time in years. R is still your rate. Okay. Those were up there yesterday for your quiz. So whenever we talk about the natural base e, okay, like I said earlier, the natural base e is irrational. It is getting closer and closer to, as x gets closer and closer to positive infinity, or as that number gets bigger and bigger, this number here continues to grow. Okay? We don't shorten it. Okay? You're done shortening pi into 3.14. You will not shorten e into 2.71 or anything like that, or 2.72. You have a button on your calculator, whether it be a scientific, a graphing, whatever you have, you should have a button for your e or for your natural base of e. So as we go, we do everything the same way if we had to multiply, or if we had to divide, or if we have to do power of a power. We treat it just like any other variable. Okay, so if I have e to the third times e to the sixth, same way if I had x to the third times x to the sixth, what would I do with my powers? I'd add them up. Okay, it's no different if I would get x to the ninth as if I get e to the ninth power. Now, e to the ninth power actually has a numerical value, but we don't really worry about that numerical value right now. There's only specific times, and mainly whenever we use interest problems, that we will worry about the actual value. If it just says to simplify it, you treat it just like any other variable, because realistically that's what it is, but it has the same value every single time. So even if I have 16e to the fifth divided by 4e to the fourth, what do I need to do with the 16 and the 4? divide them. So I'm going to have 4 on top. How about we get something that's not a highlighter? 4 on top, 1 on the bottom. What's going to happen with e to the 5th over e to the 4th? I'm going to subtract, and I'm just going to have e to the 1st, right? It's all over 1, so I can really just rewrite this as 4e. Same way if I have like a power of a power, like on C, what am I going to do with the 2? Where's the 2 going to go? It goes to everything inside here, right? So I'm going to have 3 squared. I'm going to have e to the negative 8x power. So what's 3 squared? 9, I hope. What's going to happen with this right here? What is that negative exponent going to do to my e with the base of e? Where's it going to go? Do what? Make it a fraction, or I can put it on the bottom side. Right? I can put it down here and make it e to the 8x power. So if you need to kind of have like the little sidebar here of we had the 9, and if we're still multiplying it, we would just flip it and make it e to the 8x on the bottom side, and then just multiply straight across is really all we did to get to here. That negative just moves that e to the whatever power, in this case 8x power, to the bottom side of my fraction. We treat it just like any normal variable. Okay? That doesn't change anything. So then, whenever we actually evaluate it, so if it says to evaluate and not simplify, you are going to get a numerical value. This is when you will actually round something. So probably round 2 to 3 decimal places. So all I'm going to do is just go to my calculator, and I'm just going to type in normally where it's at. If you see an LN button for the natural log, it's probably like a second and then that value. So it's probably not its own button, but it's like on a graphing calculator. It's right down here where it says e to the x power. Okay? And it's hard to see on the screen. But all I'm going to do is I'm going to hit second and then the natural log, and then it was 3, and just hit enter. Okay? Same way if you have a scientific calculator, it should be the second row or second set above the natural log. Okay? So if I have e to the 3rd, that's equivalent to basically 2.72, so on and so forth, or 2.718, all that being multiplied by itself 3 times, which is about 20.0856, whatever you want to call it. Okay? Depending on what it asks for as far as how far to round. Same way if it's negative, so if it's like e to the negative 1.5, I'm going to do the same thing. I'm going to go to the calculator, I'm going to hit second or shift, depending on what kind of calculator you have, the natural log, and then just negative 1.5. Hit enter. So then I would probably just round to 2 or 3 places and just put 0.223 or 0.22. Okay, if I evaluate, I am just basically just punching it into my calculator is all I have to do. There's not going to be a whole lot else that's going to happen there. whenever we graph it, it's no different than what we've done before. Okay? It's not going to be any different. We're still going to have the 4 things that we have to do. If A is bigger than 0 and R is bigger than 0, then it's going to be growth. Basically, if you have it to a positive power, it's still going to be growth. If it's to a negative power, if E is to a negative power, then it's going to be decay. It hasn't changed from what we talked about a couple days this week and then last week. So I still have the 4 things that I have to find. I still need to know what my asymptote is. I still need to know what my y-intercept is. I still need to know what my domain and my range are. It's an exponential function. So it's no different than what it was before when we did this. What was the first thing that you should have filled out yesterday? Domain. What is the domain of any exponential function? Negative infinity to positive infinity, right? What was the next thing that you probably filled out? This was 1. Asymptote was 2. What do we look for the asymptote? If there's any what? Any k value or any number on the back end that's getting added or subtracted. So is there a number back here that's getting added or subtracted? No, so what's my asymptote? Y is equal to 0. So then I'm going to just draw a imaginary line here at 0. It's either going to be above or below that line. So then, same way, just like I would do with a normal exponential problem, third thing would be to do the y-intercept. So whenever we do the y-intercept, remember all we have to do here is just plug in 0 for x. So if I plug in 0 for x, if I do it below here, and I have y equals 3e to the 0 power. What is anything to the 0 power? 1. What's 3 times 1? 3. So y is equal to 3. So put a point up here at 3. Now, before I graph it, bless you, what is your range going to be? It's above the asymptote, so where's your range? Where's it going from? Where is it never going to cross, and where is it going? 0 to positive infinity. Okay, 0 is not included. Neither is positive infinity. Again, right now we're looking at 5 out of 6 points because we got the domain, we got the asymptote, we found the y-intercept. Once we found the y-intercept, we knew, hey, it's above that line, so the range has to go from my asymptote up in this case. Now, in this one, because E is such a funky number and it's 2.7 whatever, if you do 3 times E, because if it's e to the first power, okay, it's not going to land. The only time it's ever really going to land on something nice and neat is probably going to be on your y-intercept. Other than that, there's probably not going to be a value for x that you're going to be able to plug in there that's going to be nice and neat and pretty to work with. It's going to be an ugly decimal that's going to be long and drawn out. So a lot of it is really from here, if you have your y-intercept, is making sure that you have the graph drawn correctly. Because the only number that's really going to be seen is going to be your value on your y-intercept. Because if you do 3e to the first power, if we just plug in 1, what is 3e to the first power? Say it again. Yeah, do you know where that is? No. Heck no, you don't. Okay? You can guess or have a pretty good idea, You can pretty well, so what'd you say, 8 points, what? So, yeah, exactly. So somewhere close to 8, right? So then all I'm going to do, it's exponential growth. It's not a negative exponent. So since it's growth, all I'm going to do is just take it straight up here and just come fairly close to that line, or fairly close to that point. The only value that you're going to be able to probably see is going to be the 1, unless we move it left or right later, is going to be the one that should actually hit on the y-intercept. There may be times when it doesn't hit on the y-intercept at a nice, neat number. That's okay. You'll just leave it in terms of e. So then like on b, where it's f of x is equal to e to the negative 0.5x, again, we find the 4 things. We find our asymptote, we find our y-intercept, we find our domain, and we find our range. First one we fill out every time is which one? Domain. So we fill out the domain, we get negative infinity to positive infinity. Second thing we fill out is the asymptote. Is there a number back here that's adding or subtracting? Nope, so it's just going to be y equal to 0. So I'm going to have an imaginary line right here at 0. Next thing then is my y-intercept. So if I do my y-intercept, I'm just going to plug in 0 for x. So I'm going to have e to the negative 0.5 times 0. What's the exponent? What's negative 0.5 times 0? 0. What's anything to the 0 power? 1. So again, I'm going to put a point here at 1. From there I can fill out my range, right? Because where's that point at? Is it above or below my line? It's above. So it's still going to go from 0 to positive infinity. Now, what's the big difference here, though? What is your power? What does your power look like? Or plug in a value. What is E if you need to? What is E to the negative 0.5 times 1? What is E to the negative 0.5 power? Really small number, right? Like almost a half, probably. Okay? So again, it's down here. You're not sure. All right? It's kind of hard to see. Maybe instead of going to a positive one, maybe you go to a negative one. So maybe you plug in a value and you go y equals e to the negative 0.5 times negative 1. What value do we get there? How much? 1.6 something or other? All that? So it's about there. What kind, is this growth or decay? Why is it decay? Because of that negative power. Okay, that negative power is going to do everything to it, and it's going to make it look something like that. You have a lot more leeway on exponential functions that have a natural base of e than you do any other ones. Because there's really only one number that's going to make this thing look somewhat presentable. The rest of it are just random, just ugly, nasty coordinates. And that's okay. But you're going to have, the biggest thing is making sure that you know, hey, that's negative. It's going to be decay. It's going to get closer to that line as it moves to the right. Hey, that's positive. So it's going to take off away from the asymptote, wherever that is. All right, last thing then. Continuously compounded interest. Yesterday we talked about compound interest where you had, that we already wrote down at the very beginning, that A was equal to the principal times 1 plus R over N, all to the N times T power. This is just regular compound interest. Nothing fancy about it. The new one is now continuously compounded interest, or if it talks about compounded continuously. Either way. The big key here is, to tell the difference between these two, is you have to have this word. So instead of quarterly, monthly, daily, weekly, semi-annually, bi-monthly, annually, whatever, if you have the word continuously, this is going to be your formula. The great thing about it is, just like compound interest, it has the same variables except for one different thing. P is still your principal. That hasn't changed. Okay? P is still the principal. R is still the interest rate as a decimal. T is still time. Okay, still time in years. So what we talked about with compound interest does not change. The only thing that's going to change here is that your formula is going to change. That you have to use E as your base. Instead of 1 plus whatever it is, your base is E. Instead of it being 1 plus R over N, your base will always be E. You have less things you have to worry about. You don't care about how many times you compound it because it says it's compounded continuously. That just tells you that you're going to compound it. You're going to have a base of E, and you're going to take it times the rate, or to the power of the rate times the time. So it says you and your friend each have accounts that earn annual interest compounded continuously. So it says balance A in dollars of your account after T years can be modeled by A equal to 4,500 E to the 0.04 T power. It says the graph shows the balance of your friend's account over time. Which account has a greater principal? So if here is your account, here is your friend's account. Okay, your friend's account is over here in yellow. Yours is circled over on the left in the formula. So the first question is, which one has the greatest principal? Any ideas? At year 0, who put in the most money? Why? How do you know? Because it's $500 more, right? Because over here, it starts at $4,000. Your friend's account starts at $4,000. Your account starts at $4,500. So as far as the first question, I have a higher deposit, principal, whatever. Next question then is, who has a greater balance after 10 years? So we can see where theirs is at after 10 years. If I go straight up after 10 years, and it's going to be between 8 and 10, I'm making a little bit over $7,000, or my friend's making a little bit over $7,000. How much am I making though? What am I going to do if I have the formula of A equal to 4,500 E to the 0.04 T power? What's the only thing that I'm missing? The T, right? So I'm going to take 4,500 and I'm going to have E times 0.04. What is T? 10. Okay? Now, what I would tell you to do, okay, or one thing that you can do, and I think you can even do this on a scientific calculator. Okay? Let me make sure. Yes, you can. Okay, so even a scientific calculator is I would always find my power first, or I would try to do the E and the power together. So what that means is if I'm going to type this into my calculator and whenever I solve this, because I don't want to round anything, I want to figure out the closest thing to the penny at the very end. So you can do it a couple different ways. The first way I would probably do it is I wouldn't type everything straight in because there's going to be grouping symbols and stuff like that you can get kind of messy. First thing I would do is take second in the natural log, and if I would have e to a power. Okay, so from there, I'm going to open up a parenthesis, and I'm going to take the 0.04, and I'm going to multiply it by 10. And then I'm going to close the parenthesis. So something like that. I get 1.49182, so on and so forth. Everybody get that number? Is there anybody that didn't get that number? Good. So from there, now I'm just going to take whatever my principal is, so the $4,500, okay, and I'm going to go hit multiply. It's going to say answer. So whatever was on that previous line times 4,500. Hit enter. 10 years, I'm at $6,713 and let's say 21 cents. Who made more money? Them or me? Right. Because what did we say? They were over $7,000. Okay. But from here, I would go slow and take e to whatever your power is and then multiply it by your deposited amount.